So section 6.3, the seismic forces on retaining walls and structures. The first part of this section is just a static portion. You're familiar, the at rest, the active and the passive conditions. And we need, for full mobilization of the active passive conditions, we need some kind of displacement. And the passive, you can see the earth pressure versus displacement, the graph. The passive is on the right side, and then the active earth pressure is on the left side, and the middle is the at rest earth pressure. So the at rest is larger than the active state, and which is less than the passive state. So more displacement required for full mobilization of the passive and the active. And both Kp and K represent fully mobilized earth pressures. So I'll run quickly through it. You're familiar with the Rankine theory, Coulomb theory, and we have also the logarithmic spiral method and displacement dependent earth pressure method for static analysis. So these are the equations for Rankine theory earth pressure for active case and then passive case. And for Coulomb theory, the main difference is you have friction between wall and soil considered. Otherwise, it has a linear failure surface. And maybe another difference is Coulomb uses a force polygon to calculate the forces, passive and active pressures. So this is just a review of the static approaches for passive and active case. And other earth pressure methods like the logarithmic spiral method, you have a more complicated failure surface, a curved surface around the bottom, and a linear surface around the top. But the analysis is also more complicated, so it has limited application for practical use. Commonly, we use the Rankine and Coulomb theories. There is also a displacement-dependent earth pressure methods. So these are more research topics and research areas. But nowadays, we use mostly softwares. So it's a full finite element analysis. So the application is limited. But they are research topics. So for dynamic case, there is a pseudo-static method for seismic pressure on retaining walls. You can use a simplified approach. The way we used it for slope stability analysis, just using a single representative acceleration and converting that acceleration into a force. We can use similarly for earth pressures also, retaining structures also. So you can go through this write-up. So the first method that we use for a pseudostatic approach is the Mononobe-Okabe method. It's developed by Okabe in 1926 in Japan and Mononobe and Matsu 1929. Later it's combined and it's called Mononobe-Okabe method. That's a dynamic earth pressure method for pseudostatic approach. This is the most widely used for the hand calculations nowadays, if you're not using softwares. Applicable for yielding walls which have sufficient wall movement to achieve fully mobilized active or passive pressure on walls. It's an extension of the static approach. The method is pseudostatic approach similar to seismic forces on slopes. Mononobe-Okabe method is a direct extension of static Coulomb theory, where pseudostatic accelerations are applied to Coulomb active or passive wedge. So basically, you can pick the Coulomb equations and incorporate the seismic accelerations, similar to what we did for slopes. So below is a sketch which represents how the Mononobe-Okabe verified their theories. So this is like a check table. This is a table where 4 foot high soil, and they applied some dynamic input, and they tried to calibrate and verify their equations. So they used conical drum help to simulate variable frequency motion on table. So you see this rope along this conical shape. So the idea is to apply some variable input with frequency. So this is the original sketch from the Mononobe-Okabe. instrumentation to verify their equations. So mononomial Okabe active dynamic earth pressure. Now the total active thrust is given by half KAE gamma h squared, 1 minus KV. That's where we introduce the KV. It's both KH and KV are introduced. Now KAE is introduced. If you see this equation, KV is a vertical seismic coefficient, and we have also the horizontal seismic coefficient in the KAE, in the active earth pressure coefficient. So this is a static case. Now we are introducing the KAE is modified. This, you see this phi angle is containing the seismic coefficient is KH by 1 minus KV. So KH and KV are the seismic coefficients, those single accelerations we pick. So it's just a direct extension of the Coulomb theory by incorporating seismic accelerations. Otherwise, the nature of the equation, if you put KH and KV 0, it should provide the static values of the Coulomb theory. So now in the force geometry also you see it. Now the KVH, the seismic forces are included. The horizontal seismic, KHW, and the vertical seismic, KVW. So all these equations are incorporated. Is that clear? So you have Coulomb theory, the static case that you know, is now it's modified for seismic forces. These are the seismic forces. These are the same seismic forces we looked at for a slope. Instead of only the weight of the soil, now we have additional horizontal force by seismic, KHW, and a vertical, because it's also getting lifted up by KVW. Is that clear? In some cases, you can ignore KV like we saw it in the slopes, but it's not a conservative approach. The equations are also similarly modified. So if somebody asks you how the seismic accelerations are incorporated, the vertical is incorporated right here, the weight is reduced, and the horizontal is incorporated in the active earth pressure coefficient. Same is true for the passive. That's the mononomial Okabe approach. So the beauty of this equation is simpler for a hand calculation. The way you do the calculation by hand in Excel or MathCAD, you can implement the same equations for pseudostatic approach using the mononomial Okabe method. Since you are already familiar with the static method, so the dynamic method, especially the mononomial Okabe active dynamic earth pressure, is pretty similar. Just incorporate the seismic coefficients. And the critical angle failure, it includes the seismic coefficients. And the coefficient C, 2E, and 1E are provided similarly. Mononomial Okabe solutions show the total active thrust acts at H/3 above the base. However, experimental check table results later show it acts at higher point under dynamic loading condition. This is very critical difference. You need to consider it. Seed and Whiteman in 1970 recommended approximately 0.6 H for dynamic component. So normally the static component, it acts at H/3, right? It's right here, let's say, for a static force. But the dynamic force is not like triangular distribution. It has some larger value at the top, the total dynamic force. So this tells us the CG for the force is at higher value. So that's why Seed and Whiteman later recommended the dynamic component acts at 0.68. The static component is still at 1/3 from the base. But the dynamic component at 0.68. But the total for the total active thrust we calculated is a combination of both static and dynamic, right? This one. It's a total active thrust. It contains the static and the dynamic together. So the total one is static plus the change due to dynamic. So the static component as h/3 from the base. It's a triangular distribution. We know that. Hence, the total active thrust acts at a height. So the resultant of both the static and the dynamic. So the static acts at h/3 from the base. The dynamic acts at 0.6 h from the base. So the net force is acting at h distance given by this. Is that clear? It will get clear in the next few slides. So this is how it is. For a slope, for retaining soil with some slope, let's say you have this dot PA, which is a static one, which is 1/3 h. And PA is the total thrust. The total thrust is acting at h distance. We don't know that h. But the change, the dynamic one, it acts at 0.6 h. So this is how it is. The change, the dynamic one, it acts at 0.6 h, the net force. The static one, it acts at 1/3 h. The static one, you already know it. But the dynamic one is recommended to act at 0.6 h. So the net, the two, it's somewhere in between, right? It acts somewhere in between. That h is where you are given with the previous slide equation, this one. See, this is a weighted average. 0.6 h, h/3 divided by the total force, then we get where the total force is acting. Is that clear? So you know, now we modified the Coulomb as the pressure. We incorporated the seismic coefficients, and we get the Monod-Piokavi method, right? And then the CG where the total force. The total force is now, the total active thrust has two components, the static component and the dynamic component. The dynamic component, Monod-Piokavi, they said it acts at h/3, but later it's verified it's acting at a higher height from the base. So Seidman and Whiteman, these are MIT professors. Through several experiments, they verified it acts approximately at 0.6 h from the base. That's what you have here. The dynamic component, it acts 0.6 h distance from the base. But the static one from Coulomb theory, it's 1/3 from h because it has a triangular distribution, right? This triangular distribution is a static one. This solid line you see here, that's a dynamic component. It's not linear. Intensity of pressure due to earthquake condition. That's this envelope. Intensity of pressure, static condition, the dot lines. Is that clear? So you can visualize it. So if you have a height h for the retaining structure, then the dynamic component acts at 0.6 h, the static component at 1/3 h. So if I ask you what height is the net force, the total force is acting, so you should find a weighted average, which is this one. Similarly, for Monod-Piokavi, for passive dynamic earth pressure, it's the same approach. The passive pressure from a static Coulomb theory is modified using the seismic coefficients Kv and Kh. Kpe is modified with phi, which had the Kv and Kh seismic coefficients, and also the weight is reduced by the Kv. When the weight is reduced, then we are losing our resistance. So we have the passive coefficients modified. It's similar, just introducing the seismic coefficients. The critical angle and the coefficients are all modified. So the total active thrust should be the total passive thrust. We are talking, this is wrong. I will modify this. The total passive thrust can be divided into static component and dynamic component. Total passive, static passive, and dynamic passive. This is the change. If you don't have earthquake, then you have only this static case. If you have seismic, now you have some dynamic component. This equation is giving you the total together. It's both static and dynamic combined. So from the total passive thrust, you have to reduce the static part to get the dynamic component. Let's see an example just for better understanding. Compute overturning moment about the base of the wall shown below for KH 0.15 and KV 0.075. So remember now we have a vertical component of the seismic now, both horizontal and vertical. But see, the vertical is less than the horizontal. Horizontal is significantly higher. So you have a dry silt soil, dry silt sand, density 1.76, phi 34 degree, and wall friction 17 degree. So the static active pressure half Ka gamma h square, you can calculate this. So first estimate the static active thrust on the wall. Because the wall is not smooth. Now if it is smooth, what do we use? The Rankine theory, right? If you put wall friction equal to 0, you should get a Rankine solution from Coulomb. So you can calculate PA, calculate your Ka, friction angle, wall friction, and put everything, and finally you have active earth pressure for a static condition of this much. I will leave the detailed calc for you. You can also look at example 11.1, reference 1. Total active thrust is now, this is a static condition only. Now for dynamic condition, we have the seismic coefficients, KV and KH, but more extended equations. You do all the math, and finally you'll come up with a total active thrust, which is a total pressure in seismic condition, which combines both static and dynamic. So let's say we got 72.3 kilonewton per meter. How much was static? 55.3 kilonewton per meter. It's an increase, right? So how much is the dynamic component? The dynamic is the difference between the two. The total active thrust, which combines seismic and static, minus the static part. So if you do that, the net force 17 kilonewton per meter, that is what? Mahadar. What's 17 kilonewton per meter? 8 is the dynamic component. The total thrust acts at a point, so we know that the static component, it acts what distance from the base? The static, this one, it has the net force, it acts how much? What's the height here? Rio, 1/3. How about the dynamic and the mood? The static component acts at 1/3, which is a PA 55.3 kilonewton. The dynamic component, we know that it acts at a higher height from the base. Who can tell me that? 0.6. That's a recommendation from Sidman and Whiteman. The mononope Okabe, they assumed initially at 1/3, but later experiments show the dynamic component acts at higher distance, right? Because that picture, you remember this, you see this envelope, because it's bulging in the upper side, that's telling you the CG of this force is higher. So that's where Sidman and Whiteman recommended at 0.6 H. So the 17 kilonewton per meter, that's a dynamic force, it acts as 0.6 H. So the total force, the total active thrust, you can get the weighted average. The active part acts at 1/3. The dynamic part acts at 0.6 H. If you weight it by the total force, then H, you would get it at somewhere in between the two, 1.98. Moment at the base is by the horizontal component, the total active thrust. If I ask you, because for design, you need to find the base force. You need to find the moments, right? Because this is, if this is a cantilever, it's going to bend. Where is the maximum moment happening? In this case, around here is a maximum moment, right? You should find, if you know where the total force is acting. Now the total force has a wall friction, so it's not horizontal purely. So it has a component downward, wall friction, and it has a horizontal component. It's the horizontal component that tries to bend the wall, right? So the moment is that horizontal component times h. After this, it's similar. From your reinforced concrete design, now you know your moment, you know forces, you can design this wall. The main difference is just getting the seismic forces and then combine it to the static, then the design remains the same. The reinforcement, the amount of reinforcement you need for a static force only is much less than when you combine the dynamic force. This is the simplest approach. You can do this by hand. You can implement these equations in Excel or preferably in MathCAD, and automatically you can get the solution pretty fast. Is that clear? At least make sure you understand it, what theoretically what we are doing, how we are incorporating the dynamic forces. This is still pseudo-static approach. We are using what? Representative accelerations, right? A single value of acceleration, maybe the peak value. If we are doing like a full time history analysis, at a very small delta t, we're going to pick the corresponding acceleration. When we finish that, then we pick the next acceleration. Pick the next acceleration. It's very time-taking. If you try to do this by hand, probably you'll quickly finish it in an hour. Implement the equation in Excel or in MathCAD, get it done. If you try to do this, you model it like in flat, and full-time history analysis is going to take time. Modeling may take you 2-3 days, and then analysis will take another maybe few hours to few days, depending on the model size. So pseudo-static approach, the beauty is it's quick. What's the disadvantage? Disadvantage is accuracy. The behavior in a full dynamic behavior of this returning structure may not be represented by a single acceleration. People try to be more conservative, but you have seen it in the slope case. Even if they design it for a factor of safety of more than 1, still failure is observed because it's so much complicated to do it with a simplified version. It's not, this geotechnical engineering, it's not as easy as, if you analyze a beam for a structure, it's easy. You have the equations, you know the exact width, you know the exact material, and pretty much with 90–95% accuracy, you can find the moments and forces and provide reinforcement. But doing that for a geotechnical structure, no, it's more complicated. We assume it, you know, a sand soil, a silt soil, but there may be something else in it. So there is more complication. But these are simpler approaches. People try to use larger acceleration to be conservative. But when you do that, there is some penalty also. You may need more reinforcement, more section for the wall. So it gets uneconomical. If you want to try to be more economical, then you have to invest in the analysis, spend more time, few days to few weeks for analysis and design it properly. And one more thing for hydrodynamic pressure or retaining structures. So far, we have seen it only for soil case, but you can have water with soil. You can have a saturated water, groundwater with a retaining structure, or you can have also water right in front of it, like a pool. If you have a pool, then you have a water, retaining structure, then groundwater and soil combined. So water, similar to the soil here, it has its own also dynamic pressure acting. In addition to the static pressure, there is a dynamic water pressure acting on the retaining wall. The same phenomena happens from this side. This water during earthquake, you may have tidal formations. There is a convective and impulsive response of water. The top portion of the water, usually it can oscillate. It can make tides like this. In some cases, it's separate from like a sloshing back and forth. When it moves back and forth horizontally, sometimes it's separate from the wall, right? In your design, if you have water in front of the return structure, what does it mean? It resists the push from the soil, right? Because this water is basically, it's a resistance. But usually we don't credit that resistance. Because at the time when you don't have that water, you don't have that resistance. So when you design it, don't consider resistance from water. That water can be used, taken out. If it's a pool, sometimes we take out the water, right? We replace it. So that instant, you don't have any resistance. What you have is, pressure from this side. By soil, by water, static, and dynamic. And on the other case, this is sloshing case, you can have also, some cases it separates itself, and in some cases it comes up like this, because it's sloshing back and forth. So there is more pressure now acting on the wall. You may think of it's more resistance, but don't use it for the design. Don't credit it. So there is a well-known analytical equation by Westergaard's theory, 1933, for dynamic water pressure for concrete dams. Water pressure due to an earthquake at depth H, at depth Y. So this is about the water pressure on this side. It can be a retaining wall, it can be a dam. But if you're looking for some analytical solution, you can use P1, this Westergaard theory, the dynamic water pressure. You have P1. P1 is this distribution. P1 along depths. Or the total P1 depth, the net. If you integrate all this, you will get 7/12 kH gamma of water H square, net force. This is the dynamic water pressure. Matsu and Ohara, 1960, have suggested that the increase of the pore water pressure on the landward side is approximately 70% of that of the seaward side. So because in this case, you don't have full water, it's saturated water. Water in the voids. So they recommended the increase on the land side, this side, because of seismic, that P2W is about 70% of what you have on this side. So if you're looking for like equations for a quick analytical representation for water condition, you can use this. During an earthquake, the force on the wall per unit length on the seaward side will be reduced, P1W, and that on the landward side will be increased, P2W. Thus, the total increase of force per unit length of that wall is, so which means during an earthquake, this gets reduced if you credit it. Usually it's taken as 0, but on this side it increases. So Siedman-Zeng method for dynamic earth pressure. There are more other complicated methods, not conventionally used, but there are more detailed analysis. The mononuclear is the most widely used in the conventional design. If you don't have to use any software for full dynamic analysis, it's very common worldwide to use the mononuclear method. Just find your KV and KH and use that modified Coulomb theories for passive and active, and you can design it. But there are other methods, more refined methods, and one of them is Siedman and Zeng method. So the mononuclear accounted dynamic earth pressure in very approximate way. It's simpler for us to use it, but it's approximate. Siedman and Zeng considered fixed base cantilever beam method to account for seismic amplification and phase difference. We didn't talk about seismic amplification so far. We're using a single acceleration value. Now, what did I say before? If you have a building with, let's say, 10 stories or 5 stories, I said, if you have a seismic input here, then is it applicable at the roof level for design? No, right? The building amplified. So the acceleration you have here is maybe 1G, but by the time it reaches here, because the building amplifies it, depending on the flexibility and the period. And even resonance may occur. If this building resonates with the input motion, so it amplifies a lot, right? 1G may end up being 5G or 10G. The same is true for dams and retaining structures. If you have input motion here, now we are assuming the same acceleration throughout, a single value. That's not true, right? Because there can be amplification through the sway. Either we should record at this level, not at this level. The higher this retaining structure, the more approximate the solution is. Or you should somehow account for soil amplification. The same way the structure is amplified, the soil can amplify too. So to avoid that approximation, Steedman and Zeng, they use a cantilever approach and see how much it amplifies. And they came up with some solution. And they compared it with Mononoke-Okabe method. With a single value Mononoke-Okabe method, see a straight line, and Steedman and Zeng, a little bit linear. But pretty much it's similar for design. From design perspective, because you account so much approximation, conservatism, this difference is not that significant. Is that clear? So even if we have more complex solution, still the Mononoke-Okabe method is not that bad. It's easy to use. Simple implementation with few hours of work. But compared to the Steedman and Zeng, it looks reasonable. But keep in mind that in more high-level researches, PhDs like that, you may be asked to consider amplification. So depending on this soil type, do you remember those impedance ratio we discussed in chapter 3? Depending on the impedance difference, there can be amplification, de-amplification, or no amplification. And it's not only impedance, it's not only material difference, even height matters. Because with height, your soil spring changes. The period changes. And you never know, the period may get close to the input motion resonance frequency. So when you start, you may pick acceleration here, but by the time it's amplified, go through the soil, it may be very close to the resonance state. That's why people designed it using pseudostatic approach in the past, even having factor of safety more than 1, but later they realized some slopes, some dams are failing. Because seismic is more complex. You can't really represent it with one single value. So nowadays, the idea is use a larger value to account for that complexity. So even if we have this, just for you, the takeaway is, yeah, Mononoke-Okabe method is not that bad. There are researches done, a lot of researches comparing, flat finite element solution compared to the Mononoke-Okabe method. Things like that. And some of you may get a research or a design opportunity to do all this. So you can come back to this section, read it in detail, and just respond to your requirement. So cantilever retaining walls, some other parameters. Cantilever retaining walls are designed much the same way as gravity walls, except that bending failures must be considered. If it's gravity wall, we're not considering bending, it's through the weight. These walls are usually like rocks with some mortar joints. We don't reinforce it. Or you may have semi-gravity wall, which may need some concrete and reinforcement. But cantilever walls, that's where you need detailed concrete design. All this reinforcement, you need to account for those dynamic forces in addition to the static earth pressure forces. And also you'll have water is really bad behind retaining structures. If you keep it there, it develops pressure, and finally it can lead to a collapse. So usually what we do is we introduce some kind of drain to remove the water. You don't want additional static water pressure. You don't want additional dynamic water pressure. So we let it out. Introduce some kind of drain, even through you see these holes. That's a common way of removing water behind retaining structures. So pseudostatic approach for other types of walls. You can have non-yielding walls. You can dynamic earth pressure for all non-yielding walls. You can see reference 1, section 11.6.2. This is a reading assignment. I'm not expecting you to submit anything on this, but you may need it in the future for research topics, for other levels. So if you come up with some need, just be aware that there are these sections. For braced walls, reference 1, section 11.8.3. Or reinforced soil walls, reference 1, section 11.8.4. Or mononuclear metal for CFE soil, reference 2, section 8.11. So just look at them. Just it's a reading assignment, nothing to submit. Just be aware that we have other advanced methods for complicated walls. Limitation of pseudostatic approach for dynamic earth pressure. We already discussed for a slope case, a choice of KH and KV is very complicated and it's not easy. So normally, assuming that retaining walls or soil behind retaining walls is relatively rigid, we can use 1 times PGA, or in some cases they reduce it 0.5 up to 50% or 80% reduction, but it's more complicated. The choice of this is really, it's not an easy job. That's one limitation for pseudostatic approaches. For braced walls, where movement is restricted, they are not allowed because it's braced, then the slope sliding or getting full mobilization is limited. There you have to use a little larger value of KH. We already discussed similar to the slopes. This is the same. Retaining structures are close to a rigid zone. You can use rigid zone accelerations, but because of sliding, it's allowed to slide through it, then reduce the value of KH is okay. But don't get surprised if your design fails. So make sure you use a larger acceleration. 1 PGA is usually what's recommended as far as it's affordable. So to avoid this, what we should do? This is a limitation in a pseudostatic approach. What we should do, if we can, and move. Yeah, more advanced analysis. So we have tools nowadays. They do better than the pseudostatic hand calculation. Hand calculation is easier, but in some cases it's difficult to choose what acceleration value. And even if you pick a much larger acceleration for design, it may not be economical. So it's better to use better tools. So nowadays we're lucky. We have commercial softwares. We can model the structure, retaining structure, and the soil together and do a dynamic analysis. But this is not also practical in most design offices. Don't get surprised if you see most design offices using only hand calculation. The beauty of hand calculation, you know what you're doing, you know your output. You need somebody experienced to do advanced finite element simulations. From the modeling to input preparation, interpretation, it's challenging. So you need people who are experienced. You need good reviewers. So we have within the campus, we have at BIT, Plaxis, and FLAG. Preparing the model is easy. There are manuals, self-explanatory manuals. You can go through it, prepare the model, mesh, introduce soil properties, and then you can run dynamic analysis. You can pick an input, and you're not going to use the input directly. Remember what we studied. You need to make sure the input is correct, right? One thing we do to make sure the input is correct is what? You need to filter out noises from the input motion and make sure, once you integrate the acceleration into displacement and velocity, you don't have any drift. So once you verify, or we call it baseline corrections. So once you verify all that, you can apply the input motion and get the output. So that's what's commonly done in most cases, but people usually use both of them: the pseudostatic approach, the dynamic approach, and compare the results to make sure that results are comparable. In some cases, you may find the dynamic approach crazy. There's something which doesn't make sense, which means something maybe in the model, something wrong, either in the input motion or in the model itself, errors. To avoid that, make sure you compare it with the pseudostatic approach and make sure you have a reasonable model. In numerical modeling, like with a hand calculation, a mass spring model can be used for water. If you have a water here, for example, sometimes in the nuclear power plant design, we have pool in the nuclear power plant. We have to design those properly. And we have to design the water itself. But there is limited application for water to model water in softwares. ANSYS can do that using Fluent. There is a software called Fluent with an ANSYS for fluid analysis. You can use that, but it gets more complicated. So usually you can use a mass spring approach. The water represented by spring, and a water mass represented by a mass. So there are two water mass. The top portion of the water, it usually sloshes back and forth. The bottom portion of the water is usually rigid. It's called impulsive mass. So MI is like impulsive mass. It's rigidly moving with the wall. The top portion of the water, it sloshes back and forth. So it's usually represented by springs and a mass. But there is, I didn't put any detail on this, but there is a reference for that. If you have to do it in the future, you can use ACI 350.3-20. This is a US American Concrete Institute. It's a reference book. It has a detail on this. If you have to design a pool or a tanker somehow with the water and to see the effect of the water with a dynamic input, you can represent the water with a spring and a mass. So the water, you can divide it into two: impulsive mass, convective mass. Convective mass is with a spring because it's flexible. The impulsive mass is rigidly attached, and you can design it more if a need arises. That completes this chapter. So main reference for this section is still a Kramer book, chapter 11, and reference to BM-DAS book, chapter 8. So you have a homework here. These problems from reference 1 and additional problems from reference 2. And it's due 2 weeks from today.